Welcome students, this is the third class of your sequential circuit. Now, in the previous class, we discussed NAND and NOR based design of SR latch, and we also discussed the problem of the previous designs, that is, the operations are asynchronous, and there are two different characteristics table for NAND and NOR based design. Now, in this new design, we have to solve this problem. So we have to make this design synchronous. That means we introduce a new control signal here. Now also that same logic level table for both NAND and NOR based design means we will implement NAND and NOR based design, but for both the cases the characteristic table will be same. So how we will achieve it? So this is the circuit diagram. This is the circuit diagram for this NAND based SR latch. Now you can see this is basically nothing but a NAND based SR latch. Now this is a extra circuit added with the previous one. Okay, so this is the clock signal which will act as a control signal. If the clock is high, then the output will change according to input. Otherwise, if the clock is low, then output will not change. Though if we change S and R, the output will not change if the clock is low. So by this clock acts as a control circuit and the whole operation becomes synchronous. Means the output will change according to the clock. Okay, so the change of output will synchronize with the change of clock. Now clock signals are basically a simple square wave. Okay, we draw the clock signal. So this is the clock signal. Okay, now here this clock is basically high means this is the high state, this is the low state. So if I receive a high state of the clock signal, this first portion of this circuit, first stage of the circuit will activate and pass the data from input to output. Okay, from this is the input and that is the output. Now when the clock is low, this will be deactivated, means no data from S will pass to the output. Okay, so suppose in this all operation the clock is high. So we show this symbol by this, the clock is high, and we make S and R both are 0. Okay, if S and R are 0 and we consider that the present state Qt is 0, then the next state will be 0, and if the present state is 1, the next state will be also 1. So that means there is no change of the output state. So that is why this is called no change condition. You can derive, we already discussed how we have to figure out this. Now in the second condition, when I make S equal to 0, that means write down S equal to 0 and R is 1, and if I consider that present state is 0, okay, so present state is 0, so obviously Q bar will be 1. Okay, then how to analyze this circuit? Suppose S equal to 0 and R is equal to 1, the clock is high. If the clock is high, means this input is receiving 1, this input also receives 1. Okay, now 0 1, so this output will be 1, output of this and NAND gate will be 1, and output of this NAND gate will be 0. Okay, if this is 1, so this Q bar is also 1, so this 1 1 gives rise to 0, no problem, and this 0 comes here, 0 0 gives 1. Okay, so if S equal to 0, R equal to 1 and the present state is 0, then next state is also 0. Okay, now if I consider Let erase all this. Now if we consider that S is 0 but R is 1, but now the present state is 1, so this will be 0. Okay, now how this will work? So obviously the clock is high means this input is 1 and this input is also 1. Okay, so here what is the output? The output is 1. Here what is the output? Is 0. So now this 0 comes here. So 0 1 means this output is 1. Okay, now this 1 comes here. So 0 and 1, output will be 1. So output will change to 1. Since the output is changed to 1, I have to repeat the operation again. So now this 1 will come here. So 1 1, the output will be 0. Okay, now this output is 0. So the 0 comes here, 0 0, this becomes 1. Okay, so if I set S equal to 0 and R equal to 1, and the present output, if I consider the present output is 1, then the next output will be 0. That means if I consider Qt is 1, Qt plus 1 is 0. So if I set S equal to 0 and R equal to 1, the output will be a reset. Similarly, if I set S equal to 1 and R equal to 0, whatever be the present state of the output, it will be set to 1. Okay, so that is what is called set state. And if I make both S and R is equal to 1, the output will be invalid. Invalid means both the output will try to get the same state, either 0 or 1. So this is the operation of a clocked SR latch, or we can say SR flip-flop. So this is basically flip-flop. Now when I include a clock with the latch, then we'll term this device as a flip-flop. And this is the characteristics table of a SR flip-flop. So if the question asks that describe the characteristics of SR flip-flop, so in step 1 we have to define. So for 1, the S equal to 0, R equal to 0. You have to explain in detail how it is no change. Now in the second step, S equal to 0, R equal to 1. Explain how it is a reset. Means you have to explain by these diagrams. Okay. Then third, when S equal to 1, R equal to 0, then explain how I said this is a set state. And again at step 4, if S and R both are 1, then how it becomes invalid. So you have to individually explain all the 4 stages. Okay. So now, so this is the operating principle of a SR NAND based SR flip-flop. Okay. Now, so this is the NOR based design. As I said, this is the NAND based design, this is the NOR based design. Operating principle will remain same, and the good thing is the characteristics table, in this case the characteristics table will remain same. Okay, so both NAND and NOR based design have same characteristics table. Okay, now this is the timing diagram. Timing diagram means I'll explain what is that. So this is the S. So this is high state, this is the low state. So this high state stands for 1 and low stands for 0. Okay. So this is the R and S. This is the clock. Okay. Now this is the Q. So how to read this? Suppose this is the positive edge. Sorry, this is the positive level. This is the high level. This is the low level. So output will change when the clock is high. So this portion, that S equal to 1 and R is equal to 0, and the clock is also high. So S1 R0 clock high, output will remain 1. So up to this, the output will remain 1. That means Q is remain 1. Now here the S changes to 0. Output is R is also 0. So both are 0 0 up to this point. Up to this point both are 0 0. So there will be no change at the output. It will remain 1. Now here since the clock is low, the output will not be affected by the change of input. Now here again the clock is high. So we have to see that here up to this R is 0, S is also 0. So up to this point no change will happen. No change is happening. So it is remain 1. No problem. Now here S is 0, R is also 0. Sorry, S is 1 up to this, R is 0 up to this, and I draw a line like that. So up to this, here to here, when the clock is high, S equal to 1, R is equal to 0, so output will remain 1. Okay. Now clock is again 0 up to this point, so it will remain, it will not affect the output, output remain 1. Now again the clock is 1 here, but S is 0 and R is 1. If S is 0, R is 1, output will be 0. So output goes to 0 and will remain 0 up to this point, because again the clock becomes low here. Now clock becomes high here. So in this case S is 1 and R is 0, output will remain 1. So this is the diagram of the Q. Okay. Similarly, Q bar is just opposite to the Q. It is very obvious because Q is the normal output and Q bar is the inverted output. So this is the timing diagram of the SR latch. This is very important. Many times this kind of questions can be asked, that describe the operating principle of a SR latch or SR flip-flop and explain with the timing diagram. In that case, you have to draw this timing diagram along with this characteristics diagram. Okay. So in the next class, we will explain the remaining flip-flops like D flip-flop, JK flip-flop, all that. Okay. So please go through the class notes and any standard books, and in the next class we will discuss more on flip-flop. Thank you, students.